general, what how elements are made. Elements up to iron are created from fusion processes inside of stars. But once you reach iron, there's not enough energy inside of stars to create any other elements, any heavier elements through fusion processes. So there are other reaction types. They're called neutron capture reactions. And there are two main types of those. The first one is the slow neutron capture process, or S process, and the rapid neutron capture process, or the R process. Now, R process reactions do occur in supernovae, and for a long time we thought that that was the primary case of them. But we found out later that the resulting elemental abundances from these supernovae don't quite mesh with the observed levels within our solar system. So we were looking for other sites where our process could occur, and one of those that was thought of was neutron star mergers. It might fill in those gaps in the abundances. And recent work has shown that this is very likely to be the case. There have been very promising observations in this due to multi-messenger astronomy. So we're going to go through all of that in the talk today, starting with just basic stellar nucleosynthesis. Just a brief overview of that. Like I said, elements up to iron are created through fusion processes inside of stars like the sun or other stars as well. There are various different steps to this process to create these elements up to iron. It starts with hydrogen fusion, the proton-proton chain, or PP chain, or the CNO cycle, carbon, nitrogen, oxygen. And all of these involve fusing hydrogen molecules to become a helium molecule. And then you get into helium fusion, the triple alpha process, which will fuse helium molecule or helium nuclei together. And then you go on through carbon, neon, oxygen, and silicon burning. All of these different steps create new, heavier elements along the periodic table. And eventually you'll reach the point of stars creating iron. But once they're creating iron, there is not enough energy internally in the stars to keep creating iron, or to keep creating elements past iron. You need external energy added to the process in order to fuse iron into something heavier than that. And since you're not getting extra energy from stars, it creates its own energy. It can't make that stuff. So those elements must be created through other means, and those are these neutron capture processes. So we'll take a look at both types of neutron capture processes with a little bit more focus on the R process. The two main types are, like I said, the S process and the R process. The mechanisms for both types are very similar to each other. There is a seed nucleus, usually an iron nucleus, starting out, and it will capture a free neutron that is flying around in outer space, which creates a new isotope of that seed element with one higher atomic mass. So if you start with iron 56, then you will capture a neutron. It'll make iron 57 isotope. If that new isotope is unstable, it will undergo beta decay, which will convert the nucleus into an element of one higher atomic number. So it'll turn that neutron into a proton, and it'll create a new element. The main difference between the two processes, the S process and the R process, is pretty much in the names, the slow process and the rapid process. It's the rate at which neutron capture occurs in these two separate processes. So the S process, or the slow process, slow neutron capture process, occurs over thousands of years. So to us, it is very, very slow. It's found primarily in asymptotic giant branch stars, so stars that are nearing the end of their life cycle, dying massive stars. And there will be seed nuclei, typically iron, that are left behind by supernovae of past stellar generations that are just floating around in outer space. And they will interact with this star, which has free neutrons floating around in it, and nuclei will capture one of those free neutrons, which creates that new, heavier isotope. Now, if that isotope is stable, it will remain as that stable isotope, which lasts until it either captures a new neutron, or until it does undergo beta decay. But if it's a stable isotope, it won't undergo that beta decay. It'll just sit there until it captures another neutron. Now, in the slow process, the time between those neutron captures are going to be on the order of decades to hundreds of years. So it'll take 10, 20, 50, 100 years before it captures another neutron. So if it's a stable isotope, it'll just stay that stable isotope. If not, it'll be able to undergo beta decay whenever it wants, or whenever it needs to. And in that, the nucleus releases an electron and an electron antineutrino, which, like I said before, converts the neutron into a proton and then changes the isotope into a nucleus of one higher atomic number. So it creates a new element that way. And the process continues on. That seed nucleus now is a seed nucleus of one higher atomic number of different element, and it can capture neutrons and create new isotopes, remain stable, or beta decay into another element. And that process continues on and on and on, lasting for thousands of years. Now, the R process is a bit different than that. It's called the rapid neutron capture process, and I think that the name doesn't quite explain how much different it is, because the slow process takes thousands of years. The rapid process occurs over seconds. There are hundreds of neutron captures per second that happened in the R process. So it's the same process. A neutron is captured by the seed nucleus, and then before beta decay can occur, before it changes into a new element, then another neutron is captured, and another one, and another one, and another one, and it keeps gaining mass from these captured neutrons before it can decay into another element. These captures continue increasing that mass very, very rapidly until it cannot physically capture any more neutrons. We call that the neutron drip line. That is the point where no more neutrons are able to be captured, and since it can't capture anymore, there is time now for beta decay to occur. It will create that new elemental nucleus, and it can start capturing neutrons again, and it will very rapidly. The same process will continue. And because this happens so quickly, this R process, it can really only occur in areas that are very, very neutron dense with high energy. So those neutrons have to be flying around quite rapidly, and there need to be a lot of them for these nuclei to be bombarded in this way with these free neutrons. And I'm going to switch now to a slide that shows a graph. This is from a book that, if you're very interested in anything with stellar nucleophysics, I definitely recommend it. It's a book called Cauldron in the Cosmos. It was kind of like my Bible when I was doing this research. My professor handed it to me and said, this is what you need to read. So there's a lot of information in there. And this graph, I'm going to zoom in here on the main part of the graph. There we go. This shows both the S process and the R process path. And we can see, let me see if I can zoom in one more time. Here we go. Won't let me do the laser pointer if I don't zoom in. So let me leave it zoomed out and I could show you here. So we can see the S process path here is much neater, much tighter. We can see that as the elements continue up, they beta decay into many smaller elements or many bigger elements. But the times between beta decay, there are a lot more zigzags in here, a lot more steps. Whereas with the R process path, we can see that it really shoots quite far and jumps between neutron numbers. And there'll be some beta decay, but it rapidly jumps up to the next one. And then there are certain areas where the number of neutrons is 50, 82, and 126, where it beta decays quite a bit and jumps up to new elements very quickly. So we can see that the R process path does have huge jumps in the mass of an atom compared to the S process path. And that will just keep going on. And so this is how we get very, very quickly amounts of these heavy elements heavier than iron. Now, both S process and R process individually are responsible for almost 50% of the elements heavier than iron that we see that are naturally created within our universe. So between these two processes, most of the elements on the periodic table heavier than iron are created. Now, where this process occurs has been really the focus of what I was looking for and recent research. Where does our process happen? What are the sites for this nucleosynthesis? And the two main candidates for that are core collapse supernovae and neutron star mergers. And we have a picture here of the Tycho supernovae and then a simulation of a neutron star merger, which I'll have a video simulation in a couple of slides here. Now, core collapse supernovae are a known site of our process, nucleosynthesis, and it was long thought to be the most probable site for the creation of these elements. Now, supernovae types 1b, 1c, and 2 could prevent the necessary conditions, lots of neutrons flying around, very, very high speeds, crashing into these seed nuclei that are created from that supernovae that's happening right there. So all the conditions are met for this R process creation. And the nice thing about supernovae are that they are relatively easy to locate and observe. It's a giant flash of light in outer space, so they're easy to pick up on telescopes. We can observe the electromagnetic spectrum information coming from them, take some images, and learn about the abundances in the elements coming from them. But when we do that, we find that the measured abundances of these R process elements in the galaxy don't really meet up with the abundances that we observe from the supernovae. They don't create enough of the stuff and send it out into space enough to make the numbers that we see within our own solar system even. And they're difficult to recreate those abundances, those measured abundances, with computer models of supernovae. So we knew that there had to be something else. There had to be something else creating these heavy elements. And one of the prime candidates for that something else that was thought to fill in those gaps was neutron star mergers. Now, neutron stars are the remnants of some supernovae of very massive stars, and they are just giant balls of neutrons. That is pretty much all that they're made of. So they are free neutrons that are flying around, and them colliding and merging into one new bigger neutron star is obviously a very extremely neutron dense event. Tremendous energy in there. It is a prime ground for the R process. The problem is that they're very difficult to locate and observe. For a long time, there was very little data on these occurrences, but this has changed recently, and I'll talk a little bit about that in the next slide. But we did manage to construct some computer models that would give us some expected yields, and that was what my undergraduate research was based on. So I was tasked with taking a program that was originally written in 1977 in Fortran and had been updated a couple times over the years, but not much. It was still only in Fortran. And it modeled the creation of R process elements in supernova. So it would take a set neutron density of a supernova event and then plot out what the abundances of these R process elements would be based on that. So my task was to take that piece of software, that piece of code, and adapt it so that it would work with neutron star information from these neutron star mergers. So I was given a group of trajectories of neutron star mergers, different paths that they would take in colliding with each other. And I had to use Fortran and some Python scripts to have the code, instead of taking the one single neutron density of the supernova, instead have it work with the constantly changing densities and trajectories of the neutron star mergers. Because as they collide, as they form into one bigger neutron star, one more massive neutron star, then there would be different densities of neutrons, of free neutrons flying around. So I had to take them and have them change with that. So it made it work over time instead of just a one single event. And we started getting some very promising results. I had worked out pretty much all of the bugs. It was working, it was taking the trajectories of the neutron star collisions and spitting out some information of abundances that seemed to match pretty well with what we were observing in the solar system. but they weren't definitive. They kind of matched, but there was still some little bit of things here and there that weren't quite there. But I had really only gotten one or two of the 100 trajectories modeled before, unfortunately, time goes on. My undergraduate research project ran out of money. I ran out of time. I graduated, and so was unable to continue. So we didn't get really to a publishable state on any of it, but our results were very promising, and other institutions had similar models, similar results. There was someone that we had heard of working on, oh, excuse me, I jumped a slide, working on that had very similar results to us, similar program out of Darmstadt in Germany. And I think she's still kind of on the forefront of this R process information. But no matter what, these were all just coming out of computer simulations. So it wasn't observed data. It was just expected data, theoretical data. So we did need to find a way to directly observe and measure the abundances of these heavy elements coming out of neutron star mergers. And we got that chance a few years ago. In August of 2017, sort of the dawn of multi-messenger astronomy, the gravitational wave event, GW 170817, was observed by the LIGO and Virgo detectors. It was a gravitational wave that was caused by a neutron star merger in galaxy NGC 4993. So it was an observed event with the gravitational wave detectors. And once it was confirmed as a gravitational wave event, that gave us a location of where this event occurred. So a few telescopes around the world pointed their electromagnetic spectrum scopes at that area of the sky and found the light being emitted from that event. So it was the first gravitational wave event to be confirmed and observed in the electromagnetic spectrum, as well as using gravitational wave detection. So really the first event of dual messenger astronomy. The observations taken from that electromagnetic spectrum data showed us spectroscopic evidence that our process material was created in that neutron star mergers. It was created with abundances that have led a lot of astrophysicists to argue that neutron star mergers, not supernovae, are the primary site for the creation of these elements, which means our solar system, our galaxy, is seeded by these neutron star mergers with these heavy elements, things heavier than iron. And just to give you an idea of the amount of elements that are created out of that. Gold is a good example. It's heavier than iron. And the amount of gold that is created in a neutron star merger is thought to be anywhere from 3 to 13 Earth masses. So 3 to 13 times the mass of Earth just in gold is created from one neutron star merger. So that's the amount of these heavy elements that are created from these giant balls of neutrons that are just crashing into each other and forming new elements. Now, because of this gravitational wave event that was discovered, there was a lot more interest in neutron star mergers, as it was the first in the sort of dual messenger astronomy. And because of that, there are some nice artistic representations of it. So we're going to watch a short clip created by ESO that shows an artist representation of this neutron star merger. So. Sends all of these newly created heavy elements flying out into the interstellar medium and seeding the galaxy with these heavy elements. Next slide is going to be here a look at the periodic table with a look at what creates these elements? What processes in the universe creates all the elements on the periodic table? And we can see here a lot of them: hydrogen, helium, created from Big Bang fusion. It's a lot of yellow. Those are created from exploding massive stars, so supernovae, sending them out. Dying low mass stars, this green, those are all going to be what is created by the S process in those AGB stars. Everything that's in purple is created by merging neutron stars. So these are all the R process elements. So there's quite a few R process elements. And this is a newer version of this periodic table with the creations on it, because just a few years ago, everything that was purple would have been marked as with supernovae. It would not have been marked as merging neutron stars. It would have been marked as supernovae creating these elements. But now, thanks to the gravitational wave discovery, we have found that they are actually created by neutron stars instead. So what next from here? We've discovered that neutron stars do create these R process elements, but where do we go from here? And although the findings of this gravitational wave event are very promising, obviously more data is always going to be better. So what we do next is we use more of these gravitational wave events as they're detected, use them to observe these neutron star mergers, allow us to gather more data on them, see if the abundances match up, see if they are consistent with the amount of material released in each neutron star merger. Are there other sites that are available or are prominent for this? Stuff like black hole mergers or neutron star black hole collisions. And then how do we obtain better measurements of these hard to find events? So if they are a black hole merger that is releasing elements, not only how do we track that using gravitational waves, but once we do, how can we take a look at it? Do we have the equipment? Can we make the equipment to get a better look at what is coming out of these tremendous explosive collisions?
Wayne?
Yes.
We have a question. Somebody asks,
yes.
So are all of the elements created in space? Is nothing created naturally on Earth?
So if you look at this one here, everything that is this sort of grayish, greenish color here, along here, are created in labs here on Earth. They're only created in labs. Now, things being created naturally here on Earth, all the stuff that we have here on Earth comes from being created in stars and then flying out throughout the galaxy. So created in supernova, created in the Big Bang, created in neutron star mergers, and then sent out and gathers up as planets and stars are formed in the universe. So pretty much anything, only these things that are in gray-green-ish, I would call this color, those are the ones that are created here on Earth in labs. We can also have some creation of other elements on the periodic table in things like nuclear reactors. Nuclear bombs will create elements as well sometimes. But as far as any sort of nominal abundance of these materials being created, not here on Earth. They are created in space from stellar events. See. Oh yeah, so then what next is to find better measurements. And then if you are interested in this topic, in our process, or anything to do with stellar nucleosynthesis, nuclear astrophysics, here are a couple of resources for you. One of them is the Cauldrons in the Cosmos, the nuclear astrophysics book that I was recommended to read, and I highly recommend it if you are interested in this. It does have some really great information. The math in it can be a little bit heavy at times, but outside of the math, the information is still really, really good. And then the paper here, Neutron Star Mergers as Sites of R Process Nucleosynthesis and Short Gamma Ray Bursts on the Archive. It's from 2018, and it really takes a deep look at the information coming from the 2017 gravitational wave event. And it uses that as its jumping off point for measuring abundances and explaining that neutron star mergers are very viable sites for this. And as always, you should definitely visit us at the Cernan Center. I know you can't visit us in person now, but we do have some resources on our website, so please check that out, including the Abrams Sky Calendar you can download. If you know anyone who is teaching or running a summer camp and they would like to do a virtual field trip, we are doing those. And as always, maybe not right now because it is raining very hard right here, but get outside and take a look at the real sky. There's always good stuff to see, even if you are here in the city like I am and can't see much of it. It's still there and you can take a look at it. But that's about all for my PowerPoint here. And then, I did just get a message here. Which professors are working on this subject? So I worked with a professor he was out of UIC. I'm not sure if he's still there because it's been about 5 years. His name was Claudio Ugalde. And he was my research advisor for this project. He wasn't working directly on it. His personal research had to do with more experimental nuclear physics. Mine was kind of a side project of his he was interested in. The group out of Darmstadt that was working was run by a woman named Arcones, I believe. I'll have to double check that. But yeah, that were the two people who I knew of who were working on this. There are many other institutions who are working on it as well.
So
yeah.
Wayne, do you think that the science has changed significantly since Cauldrons in the Cosmos?
Since Cauldrons in the Cosmos, well, that book was written in 1988.
Okay.
So it is a bit older.
Will have changed.
The science has changed, yes, but the math hasn't really changed. The basics in there are still good. So just the so the science has changed a little bit, but the math and how these things are determined is still correct. It's just the sites of where it happens has changed a little bit. And that's just for the sort of R process and S process nucleosynthesis. When you go into some of the other stuff, I'm sure that there are other areas in the book where the science has changed quite a bit more significantly than the R process discoveries have. But yeah, that's about all I have. So Chris, would you like me to turn it back over to you?
Why don't you hold on there just a minute?
Oh, yeah, absolutely.
I was going to find out if people have questions. And so if you think you have a question and you are comfortable unmuting yourself, you can do, I can unmute everybody, but sometimes that's opening the floodgates. If you have a question, go ahead and speak up. It's awfully quiet out there. I'm going to take a chance. I'm going to just go ahead and unmute everybody. Now, I've unmuted you, but you also still have to unmute yourself. So if you have a question.
Okay, me, Claire.
Okay.
How often do neutron stars collide? Are they that plentiful that they run into each other?
Well, you know what? I had just looked up the different gravitational waves. So that was why it was thought to be that supernovae were the primary source, because we know supernovae happen, and we know that they happen at a relatively numerous amount. There are quite a few supernovae throughout the galaxies, throughout the universe. Neutron star mergers we weren't quite sure of, but we knew that they did happen, and that's why we thought maybe neutron star mergers were just a backup site for this process. But now, since we're seeing the amount that comes out of them, out of one of them, we think it's the primary source of them, and we think that they might happen a lot more often than we did before. So like I said, that first neutron star merger, GW 170817, was the first one detected that was dual messenger astronomy. And since then, I believe they have found a couple more using gravitational wave events.
So, are these neutron stars, had they been in orbit around each other and the orbit decayed, or did one snatch another one, or how did these two meet?
Usually it's because they're in orbit around each other and the
Okay.
orbit decays. Yeah, from they orbit each other and then they just orbit decays, and they crash into each other. They merge together.
Okay.
What causes the orbit to decay?
So just gravity, basically gravity pulls them into each other, and they end up crashing.
And does that form one new star, or does that destroy both of them?
So as we saw in the short video clip, it does result in a tremendous explosion called a kilonova, but what's left behind is one new neutron star. And I can play that again, although the music on it was kind of loud.
Yeah.
I can actually mute your, well, you won't be able to talk over it though if I mute Wayne's shared sound.
Yeah, let me see if I can just mute it this way. There we go.
Thank
I think
you.
that worked. Yeah. So yeah, here in the video clip, you can see the orbit decays as they go around each other. Gravity is just pulling them into each other. And these are very, very massive objects of their own right. They're very dense neutron stars. So they both have very strong gravity. They're going to pull towards each other. And then they'll merge together. This is where all of those neutrons are crashing into each other, creating those new elements. And even now, as there is this kilonova explosion, it is releasing those new elements out into the interstellar medium and spreading them out throughout the galaxy. And what's left behind, you can see there, is just now one neutron star left behind.
Chris, can
Yes.
you hear me? Oh, I'm sorry. I got disconnected. Our whole, cable network here got, essentially wiped out. So I'm rejoining through my iPhone. But, I apologize. Thank you so much for
Yes.
for proceeding. I would just like to mention that the next meeting of the Chicago Astronomical Society is scheduled for Friday, July the 24th. We will let everybody know once the meeting has been firmed up.
Okay. And the intended location of that July meeting is still the Space Center, although we will know as we get closer whether or not that can be in person or if it will be online again. And I was kind of worried about you there, James, because I saw you disappear and then you tried to get back on. So I was rooting for you.
Yeah, unfortunate. I got no cable, no TV, no internet here. So, I decided to try my iPhone, and I was able to hear most of Wayne's talk. Unfortunately, I could not get video.
Well, it's been recorded, so as soon as we're able to get it posted, we'll let everybody know.
Thank you.
Okay, thank you.
Is there any other business that we...
Where did you say this was going to be posted?
Well, I need to determine where that can be posted. I'll post, if it's all right with you, I'll post a link to the Cernan Earth and Space Center Facebook page with the link, and I can also email that out to members.
Okay.
While I'm thinking about it, I had a couple of questions for Wayne before he tries to bail on us.
Sure.
So Wayne, there were a couple of things, and I don't want, to insult anybody's intelligence, but there might have been a couple of things that you sort of threw around out there, and I'm not sure if everybody was fully aware of things like LIGO, Virgo, ESO, those kinds of things. Are there any questions about acronyms and other kinds of details of the talk that might have escaped others? Was everybody comfortable with all of the,
Yep.
Okay. I just want to make sure that the acronyms didn't get by you and go, what was that?
Yeah, I absolutely understand that. And yeah, so LIGO and Virgo are gravitational wave detectors. ESO is the European Southern Observatory. They create a lot of really cool content. You should check out their website. They have some really cool videos. But yeah, if anyone has any questions about anything, if there's anything that I mentioned during the talk that you would like to know more about, or didn't quite grasp my meaning, please feel free, let me know, and I will do my best to clarify.
That was a lot to digest, but very cool that how our knowledge and understanding has changed, and the difference between the S process and the R process. When you said there was going to be a difference between the two, you know, on the tune of, what was that, you know, hundreds of years or thousands or millions of years between, to seconds. I wasn't expecting it to be quite that.
Yeah. Yeah, it's a big jump. It goes from, you know, hundreds of years between neutron captures to hundreds of times per second.
Wow. Does anybody else have any questions?
No?
Can you repeat what you just said? What happens 100 times per second?
Neutron capture.
Yeah, so in the R process, in the rapid process, the elemental nucleus will capture another neutron hundreds of times per second. Whereas in the slow process, the S process, it'll capture another neutron once every 100 years or so.
Jonathan, is there anything you might want to add to this? Because you had some pulsars, neutron stars, and gravitational waves in your research, as I recall.
Can you hear me?
There you are.
Yes.
I figured you could unmute yourself.
Yeah, I guess the only thing I would add is just to mention that these neutron mergers are not something we've been able to see in the past. They are very much a new kind of astronomy, and that comes from the gravitational waves we can detect at LIGO and some other sites right now. So the recent hypernova of the two neutron star mergers we've been able to observe, and we've been able to observe them with our regular telescopes too, after they were detected and sort of the location was narrowed down using the gravitational wave observatories. Those in combination with each other are giving us a whole bunch of new information about these processes, where all these heavier elements in the universe come from, and how common these mergers are. So this is all pretty new stuff, pretty cutting edge stuff right now. And I expect we'll be hearing a lot more developments for this type of thing in the next decade or two as gravitational wave science gets more and more developed, and we get a little bit better at catching these events as they happen.
Wayne, you want to stop your sharing there? Just
Oh, yes. Yeah, absolutely.
I had you go ahead and leave it where it was in the event that you were going to need to jump back to some video. So while I'm thinking about it, anyway, Wayne, thanks a lot for putting together the talk. I learned
My
a bunch
pleasure.
of stuff, and it's not my area of expertise, so I now have a couple of questions or things. Cauldrons in the Cosmos. 1988. But sounds like good stuff. While we've got everybody here, James, Mr. Kuka, did you get to say everything you needed to?
Yes. By the way, I'm a big fan of Cauldrons in the Cosmos. I highly recommend it.
Okay, well, that's good. James, do you have any idea what the talk is for July yet? Or is that sort of dependent on if it's in person or online?
Yes, everything is totally up in the air, Chris. I really have no idea. We have a number of alternatives, but once we get something set, hopefully within the next week or so, we'll notify all CAS members and also post the information to our website.
Okay. And you let me know, and we can host another meeting online if we need to. And there's always good stuff to talk about. We can also take a little tour of what's up in the night sky. As we were talking about earlier today, we're going to have planets in the evening sky in the late summer and into the fall. Jupiter, Saturn, Mars at opposition, lots of good stuff coming up. So one of the things I'm hoping to be able to do in the latter part of the summer is to see if we can do a star party, do it safely, social distancing, with some cool stuff outside. Just to get out and do something and be able to look through telescopes, again, in a safe manner. But anyway, Wayne, is there anything else you want to throw in since you've been there thinking?
No, I think that was pretty much about it.
Okay. Is there anything else, Mr. Kuka? Does anybody else want to jump in? You have
No,
good...
Chris, just thank you so much for hosting this. And we may want to put the bite on you again for July.
That's what we're here for. So, and no, you're not putting a bite on me. This was fun. And if anything, I'm just glad you guys weren't out driving in this weather tonight. So that's, yeah.
And I apologize for getting disconnected.
It happens. It happens. I saw you pop out and I saw you pop back in. So I was, but anyway, everybody, hopefully we'll get we've had some beautiful skies. The moon is nice. Had a bunch of really nice passes of the International Space Station. As Wayne mentioned, on the Cernan Earth and on the triton.edu/Cernan, you can download for free the monthly sky calendar from Abrams Planetarium in Michigan, and a great resource which includes, if you have not seen those before, hang on here. I have my demo versions right here. Let's see. Hang on. All right, start video, please. There we go. Anyway, greatest invention in astronomy after the telescope is a star chart. No batteries needed. Handy dandy tool, lets you find out what's up in the night sky. Just rotate it so that you're facing the correct direction. And some of it is teeny tiny print, but the sky calendar has all sorts of great details, like, can you go out and see Mercury, one evening this month? We don't always get good appearances of Mercury, but sometimes. So this is a really handy tool, and they have graciously allowed us to distribute these all over the place during the pandemic. So that's a really handy tool. And you can go out and look at the sky and be safely social distanced. So let's hope for some more clear skies. Anyway, I'm not going to hold everybody hostage. If you want to stick around and talk for a little bit, you're welcome to. If you want to leave on us, I think we've gotten to the end of the program. I'm going to stop recording so you can make jokes. Let's see here.
Well,
hang on here. Hang on. Okay. Oh, nope. Just somebody else thanking Wayne for his presentation. So,
yeah.
You're all very welcome.
Well,
Thank you.
all right. Thank you, everybody.